Welcome back to CS111. In this lecture, we're going to take a look at some different algorithms we can use to go and sort data that we have stored, generally in an array, but sometimes also in a linked chain of nodes. As you'll find as you get more involved with programming, a really common task in computer programs is to go and sort data. Sometimes it's just for the convenience of humans who might be using the program. Maybe we want to be able to go and sort results by a certain parameter. But sometimes sorting also has applications for helping to prepare the data for further processing. So, for example, if we're trying to do a binary search on data, it can be helpful to go and have the data pre-sorted. So between, things for the benefit of humans and things for the benefit of computers, there's a lot of reasons why we might go and sort our data. Normally, we'll go and sort in one of two orders. And there's either going to be numeric order, so we're going to go through and have values that are higher numbers or lower numbers, and we're going to sort those in order, or in alphabetical or lexicographic order. And that's something that can vary a little bit depending on what language the computer that your application is running on is actually set to use. When we go and sort our data, we're making a series of comparisons between different pairs of items. For each item, we need to figure out if it's smaller, equal to, or larger than another item that we have in our data set, so that we can go and set them in their correct relative locations to one another. In order to go and do that comparison, we need to have some way of going and figuring out if the value of one particular variable or object is less than, equal to, or larger than another object. If we're going to go through and try to compare primitive types, so things like ints and doubles, it's pretty easy for us to go and do. We can just use our standard operators, so less than, greater than, the equality, equal operator. Those are going to go and work on our primitive types. Things start to get a little bit more complicated when we're going and dealing with reference types objects. And this can be a little bit of an issue because when we're working with data structures, we're generally using generics, and because of that, we have to deal with reference type objects. The standard solution here is to make sure that the objects we're storing implement the comparable interface, which means that they're going to have a compare-to method that allows us to go and figure out how two objects stack up relative to one another. If we're using one of the common reference types that's built into Java, so like it's primitive wrappers for like integer and double or string, things like that, compare to is already implemented. If we're going and creating our own classes, we'll generally have to go and implement a compare to method ourselves. And we saw in a previous lecture how we could go and do that. But we need to have some way to go and compare our values so that we can sort them, and implementing the comparable interface is the normal way to go and do that. When we go to sort data, we normally try to do what's known as an in-place sort. This is where our sorting algorithm goes and modifies the values in the existing array or data structure that we provide to it to be sorted. This goes and saves memory versus going and creating a new array or new data structure to go and store the sorted results in. When we do an in-place sort, we do have a little bit of a complication because, for example, if I'm sorting here and I need to go and swap the contents that's in element I with what's in element J to go and sort, in Java, there's no way for me to do that directly in one shot. Some cases, with Python, I can actually go and do that. But with Java, I can't. So what I have to go and do is create a temporary variable that's going to temporarily hold the contents of one of the elements as I shift things around. So you can see on screen here when I'm trying to swap I and J, I'm going to go and create this temp variable that's going to store what's in I initially. We're going to take the value in J, copy it into I, and then we're going to take what's in our temp variable and put that into J. So we have a little bit of memory required for this, but generally speaking, especially with an iterative implementation, the memory requirements for in-place sort are pretty minimal. When we're sorting data that's stored in nodes, you might think that we might just take our nodes that we need to go and swap or move around and just go and update the links to hook them up to whatever their new positions are supposed to be. As it works out, that's actually a really complicated way to go and do things, especially if you're working with singly linked nodes. It can be hard to go and figure out what other nodes you need to go and update, especially if you don't have the ability to go in both directions from a node. What you normally see when you're going through and sorting items that are stored in nodes is that rather than trying to move the nodes, what we do is we just swap the values that are stored in those nodes. So the nodes stay in the same position, their links stay the same, it's just that the values that they actually contain go and change. When we're going and doing this, we basically follow the same pattern as swapping with an array. We're going to need a temp variable. It's just that rather than going and accessing array elements directly, we're going to go and use the get and set methods to go and manipulate the values in our list or whatever data structure we're working with. With those basics out of the way, let's start taking a look at some sorting algorithms. While there's a number of different ways that we can go and sort values, some of the most common approaches basically mimic what we might do if we as people were manually going and trying to sort things. For example, let's say that I've got a set of playing cards. So I've got 2 through 9, and then I've got Jack, King, Queen, and Ace. I want to go and sort those in order. Chances are, if I'm going to go through and start sorting things, or maybe if I've just got a set of paper, what I might go through and do is just kind of start from the front of the deck and go through, pull out the next card that I haven't sorted yet, figure out where it's going to go in my sort order here, and put it there directly. Kind of like what I'm showing here on the screen. These are generally some of the easiest approaches for us to understand how they work, and also they're normally some of the easiest approaches for us to go and code up. We're going to be focusing on these sorts of approaches with today's lecture. Just be aware that some of their simplicity does come with a cost. These are not necessarily going to be the most efficient ways for us to go and sort our data. This animation that we've been looking at is for a simple type of sort known as Insertion Sort. Insertion Sort goes and takes an array or data structure that we're going and storing data in, and it divides it into two pieces. First is going to be values that we've already sorted. Second is going to be values that we still need to sort. It's considered what's known as an in-place sort because we don't have to go and allocate a big chunk of memory otherwise to go and store things as we go and sort. We'll have a little bit of memory required because we'll need a temporary variable to keep things as we go and shuffle stuff around, but other than that, it doesn't have large memory requirements. This is actually considered, from a memory standpoint, a pretty efficient sorting algorithm. As you can kind of see with this animation here, we're starting at the front, and initially we just have a single item in our sorted portion, the very first item that's there, because if we only have a sorted section of one item, it's automatically sorted. What we're going to do then is take a look at the next item, and then we'll go and shuffle stuff around so that our first two items are sorted. Then we'll take a look at the third item. We'll go and shuffle stuff around so that the first three items are sorted, and so on until we get all the way through our entire data set. It's going to take n-1 passes, where n is the number of items that we have, in order to go and get everything sorted into the location where it needs to be. Let's go ahead and take a look at how we can implement this in Eclipse. Here in the Insertion Sort class, I've provided you with a main method that goes and creates an array of primitive ints, and it goes and stores random numbers in those. There's going to be 20 of them. And down here we have code that's going to go through and print out the values of the array before we go and sort, and then we'll have a place where we'll go and call our sort method, and then we'll go and print out the values afterwards to see how things have changed when we sort. We're going to go and implement insertion sort in two different ways. One with an iterative loop-based solution, and the other using a series of recursive calls. Let's go ahead and start off with the iterative solution first. Let's go and start off by creating our new method. We're going to make this method be public, and it's also going to be tagged as static because I don't want to have to create an instance of this class in order to be able to call it. We're not going to rely on the values from any fields, so there's no real reason for it to be tied to a particular instance of the class. Static is going to give us more flexibility. Our method here is going to return void. We're actually just going to go and sort things inside the array that we're going to be taking as an argument here in a moment. That array itself will end up being sorted, so we don't need to return anything. We're going to call this method Iterative Insertion Sort, and for our argument, we're going to take an array of primitive ints. The approach that we're going to use here with this method, we'll go and use like the greater than, less than type operators to go and compare values. So this approach will work for any of the primitive number types, so like int and double. If you're dealing with a reference type, so something like string or your own custom class, or one of the wrapper types like integer and double with a capital D, you're going to need to use either the compare2 method or one of the things we're going to be looking at later, Comparator with the objects.compare method to go and deal with those reference types. Like I said, we're going to be looking at those with some other sorting algorithms later in this lecture. For now, we're just going to focus on primitive types. Inside the method, we're going to go and have a loop that's going to go and basically sort each of the items. And for our loop here, I'm going to use a for loop because I know up front how many iterations we're going to need. I'm going to create a variable I to serve as my counter, and I'm going to start it off at 1. I is basically going to keep track of which of the elements I am trying to sort right now. If I'm going through and starting off, I don't want to go through and necessarily sort element 0 at that very beginning, because if I'm just trying to sort 0, I don't have anything to go and compare it against. I need to really have at least 2 elements to go and compare so I can figure out how to place the values relative to one another. So we're going to go through and start off with I equals 1 so that the first time through we've actually got at least 2 values that will end up sorted when we're done. We're going to go ahead and loop while I is less than sortArray.length, and that's going to go through and essentially represent the number of items that are in our array. Each time through, we're going to go ahead and increment I. The way insertion sort's going to work is that we're going to go and take the value that's at our sort array element I, and we're going to go and figure out the correct place to insert it in the sorted portion of our array, which is going to start at element 0, and it's going to go up to and including that spot where we're taking the element from, so it's going to be 0 through I. For this to work here, we're going to actually go and capture this value in a temporary variable, because what's going to happen is that once we find the correct location to go and insert it, anything that is in that element and anything to the right of it in the sorted portion, we're going to scoot to the right by 1 element. So the original location, I, is going to get overridden. So we need to have a variable to keep track of it so that we don't lose that value when we go and overwrite things. So I'm going to create this var here that I'm going to call insert value, and I'm going to set it equal to sort array sub I. Next, we're going to start with the element that is immediately to the left of I, and what we're going to do is go and compare that element to I, with the idea that we're trying to find the location where I is going to go through and work. to be inserted. As we go along here, we're actually going to go through and take whatever is in our element that we're looking at, and we're going to slide it to the right one spot. And we're going to do that until we actually get to the point where we're going to be inserting I. The idea here is that we're going to have to move stuff out of the way to free up a location for when we eventually go and insert I. So we can keep track of which element we're currently looking at. I'm going to create this current index variable, and I'm going to initialize it to I minus 1, so the position immediately to the left of I. And then we're going to go and have a loop that's going to go and move values to allow our insertion. I'm going to do this as a while loop because I'm not sure how many iterations this loop is going to have to run for. There are two conditions that I need to check for. The first one is going to be that current index is greater than or equal to 0. I want to make sure that when I'm going and trying to sort things, I don't overrun the beginning of my array. The other condition is going to be logically ANDed with that, and that's going to be that the value that we're trying to insert is less than what is at sort array sub current index. So basically, what we're checking to see here is the value that we want supposed to go to the left because it's a lower value than what's currently in an element. If so, then we're going to go through and actually take the element that's there now, move it to the right, slide it over, and then we'll go and advance. Eventually, when we get to the point here where insert value is either equal to or greater than what's in sort array at current index, that's where we're going to go through and insert the new value. And that's actually going to get inserted to the right of current index. You'll see what happens with that. So for our loop here, what we're going to do is move the existing value to the right by one element. So I'm going to say sort array sub current index plus 1 equals sort array sub current index. So we're sliding things over, and then we go and update our current index. So now we're going to go and look at the next element to the left. So we're going to do that by decrementing current index. Once we've fallen out of the loop, it's either that we've gotten to the very beginning of the array and there's no more places to check, in which case we'll go through and insert the new value in element 0, or that along the way we've found a case where our new value is going to be greater than or equal to what's going to be to the left of it. So we've actually found the correct location for it to go and be inserted. So there, we're going to go ahead and insert the value at the identified position. And here I'm going to say sort array sub current index plus 1, and that's going to be equal to my insert value, so that temporary variable that I went through and kept track of stuff with. So this is going to go through and loop basically for n minus 1 times. If we go through and look at, we're starting off with 1 and we're looping while we're less than the length, and of course being the number of items that we have in our array. And it's going to go through and just march its way down, starting at element 1 down to element n, and it's going to go through and sort all of those into place. Let's go ahead and provide some Java doc for our method here. We're going to say that this iteratively performs insertion sort, and sort array is the array being sorted. Insertion sort can also be implemented recursively, so let's go ahead and code up that sort of implementation. We're going to use our same array of primitive ints for our data to be sorted here. For the recursive method, it's going to be a protected method here because this is actually going to be an internal sort of helper method. We're going to create a public-facing method that'll be used to kickstart the recursive process. That's going to make things a little bit easier for end users because they won't have to keep track of the correct argument to go and pass for the second argument that we're going to have here. This method is going to be static. We don't need to go and create an instance of the class to use it. And it's going to have a void return type because we'll go and sort on the array that's passed in directly. I'm going to call this method recursive insertion sort, and it's going to take 2 parameters. The first is going to be an array of primitive ints that we're trying to sort. We're going to call that sort array. And then we're going to have a second parameter that's going to be an int, and that's going to be the end index for what we're trying to sort in this pass. So we're going to assume that we're going to start at index 0, and we're going to go up to whatever is specified for end index. The way our recursive calls for this method are going to work is that with each call, we'll go and subtract 1 from end index. Eventually, we'll get to the point where end index is 0, and that's going to be our base case, because if I get to where I'm starting at index 0 and I'm stopping at index 0 with my sorting, I've only got one element. It's automatically going to be sorted at that point. Let's go ahead and write an if statement to take care of our base case. So we're going to say that it is that we are only sorting index 0. I'll write an if statement here, and we're going to say if end index is equal to 0, then we're just going to go ahead and return. And this is a void method, so I don't actually return a value, I just return. Right after that check for the base case, we're going to actually go and put our recursive call. And we're going to go through and sort essentially the first end index minus 1 elements. And this is going to go through and essentially sort things here by the time our recursive calls work, where first we'll go through and sort from 0 to 0, which is our base case, but then we'll sort from 0 to 1, 0 to 2, and so on until eventually with this, when we get to the back to the very bottom of the stack, will be where we're sorting the entire array. For our recursive call here, it's a static method, so I'm going to go and call insertion sort dot recursive insertion sort. I'm going to go and pass the sort array that we're trying to sort on, and for that second parameter, I'm going to say end index minus 1. That way we're going and working our way towards the base case. The rest of this method is going to look pretty similar to what we did with our iterative implementation. We're going to go ahead and create a temporary variable to try to keep a track of what we want to insert for our insertion sort. So I'll say var insert value equals sort array sub end index here. Then we're going to go through and determine the position that we want to compare, starting at the right and moving left. So we'll say int current index equals end index minus 1. If you notice here, essentially end index is replacing I from the for loop we had. Basically, this recursive call goes and eliminates the for loop that was in the previous version. We do still have a loop in our recursive implementation. And that's not uncommon to have still some loops inside of a recursive method. Sometimes there's stuff that you just really need to loop. I could go through and make this be another recursive call, but then I'm going to go and split out another method to go and handle that portion of things, and it's just going to make the code more complicated. I'm going to go through and actually keep this as a while loop because I think this is going to be a little bit easier way for me to go and have manageable, understandable code. So we're going to go and basically loop to move values to allow our insertion. So it's going to be the exact same type of while loop setup that we had before. We're going to go through and loop while our current index is greater than or equal to 0, and while the insert value is less than what's in sort array sub current index. And if both of those conditions are true, we're going to go through and take the value that we're looking at and move it to the right by 1 position. So I'm going to say here sort array sub current index plus 1 equals sort array sub current index. And then we're going to go through and update our current position to move left by doing current index minus minus. Once we get out of our while loop, we're going to go through and insert our value at the identified position, and that's going to be sort array sub current index plus 1, and we're going to set equal to insert value. I'll go ahead and drop in some Javadoc, and then let's take a look at creating a public method that will serve to kickstart our recursive calls. With this public method, all we're going to have to do is provide the array that we're going to sort. We're not going to have to keep track of what to specify for the end index. So that'll be easier for end users to work with. It's going to be a public method, and it's also going to be static, and will return a void. I'm going to go through and call this Recursive Insertion Sort. And this one's just going to have that single parameter, and it's going to be the array of primitive ints that we're trying to go and sort. Inside, we're just going to have a single line that'll go and call the other version of Recursive Insertion Sort. So I'm going to call the name of my class Insertion Sort dot Recursive Insertion Sort. The first argument is going to be my sort array, and the second argument is going to be what my end index should be. So I want to use the highest actual index that is inside my array. So that's going to be sort array dot length -1. And then I'm just going to take the Java doc that I had from the protected version of this method, and I'm copying it and pasting it in place. And then I'll just go through and drop off the end index param, since that one does not exist on the public version of our method here. Now that we have these methods coded up, let's go ahead and call them. We'll start off with the iterative method. Up here in my main, where I have the comments about calling the sort method here, let's go and call insertion sort dot iterative insertion sort, and I'm going to go and pass it the numbers array to sort. And we'll go ahead and run this code. So you can see I've got these values here before the sorting, and they're not in any particular order. They're just whatever random numbers we got. Afterwards, you can see that things have been sorted in ascending order. And there's some cases where I have numbers duplicated, but that's okay, because if I go through and take a look at the original data set, you can see, for example, I have two 21s there. So that's okay if stuff gets duplicated. It was duplicated in our original data. We can also go and call our recursive method. So I'm going to comment out that original call. Now we'll call insertion sort dot recursive insertion sort, and I'm going to use the public version of the method here, and I'll go and pass it numbers as the array to sort there. Go ahead and run it. You can see that this runs same as what we had before in terms of getting results. We're getting an original array that is unsorted, and then after we go and call our method, things get sorted into place. Taking a look at insertion sort, we can see its time complexity for 3 different scenarios. Our best case is going to be where the array is actually already sorted. In that case, we're looking at big O of n time, just because we do have to go and make that many passes over our array to check. The average case assumes that essentially our data is not sorted right now. That's going to be big O of n squared time, because we have those 2 nested loops here where we're going through and shuffling things around. So each of those is basically going to run in big O of n time. N times n is n squared. Our worst case scenario is going to be where the values are sorted, but they're sorted in the opposite of the order that they're supposed to be. That's going to require the most number of moves to go and shift things in their correct positions. That's also going to run in big O of n squared time. Taking a look at some of the pros and cons of insertion sort, we find that its best case performance is better than some of the algorithms that we're going to be taking a look at here. Its worst case is similar. Its average is in the same ballpark with big O of n squared, although sometimes insertion sort ends up actually requiring somewhat fewer moves than some of the other algorithms. Insertion sort performs pretty well when we have small arrays, and it performs really well when we're looking at our best case scenario, which is that things are already sorted. Insertion sort's also pretty easy to go and apply when we're inserting new values. We can just go and insert them essentially into their correct position, which is basically what insertion sort does. The big negative to using insertion sort is just that when we go and work with large arrays, it can take a while, and that's going to be a problem that's common to a lot of the different algorithms that we're going to be looking at in this lecture. Next, let's take a look at selection sort. Selection sort also goes and makes n-1 passes over our data set, but it behaves differently than insertion sort. What selection sort does is on each pass it goes and tries to find the smallest value that has not been sorted yet. It's then going to go through and swap that value with one of the values at the front of the array. So basically, if we go through and assume that I is a 1 base index as opposed to a 0 base index for our values here, the ith smallest number gets put into the ith position. So the first smallest number goes into the first position, index 0. This is also an example of an in-place sort. We just need a temporary variable to keep track of the numbers as we swap, but otherwise we just go through and update values using the existing array or data structure in their positions there. Let's go ahead into Eclipse and see how we can code this up. Let's start coding our iterative implementation here. This is going to be a public method. It'll be static. We're going to have the same restrictions on our tgeneric type as what we've done before. So we have to work with the comparable interface, and we're going to return a void from this method. And let's go ahead and call this iterative selection sort, and we're going to go and accept an array of type T that we'll call sort array. Inside our method, we're going to go and create a for loop that's going to drive the number of passes that we need to make. For my for loop here, I'm going to go and create the counter I, and I'm going to initialize it to 0. And I'm going to loop while I is less than the length of our array -1. And the reason why I'm doing -1 here is that in what would otherwise be the very last pass, if we went the full n times, there would only be one unsorted item left. And sort of by that point, by default, it is sorted into where it belongs. So we don't need to do that very last pass. That's why we're going and subtracting 1 here. Each time through, we're going to go and increment I. Inside the for loop, what we're going to do here is find the minimum value for this pass. We need to go and have a variable to keep track of what position that's in. And so we're going to create this var min index here to do that. And we're going to initialize it to I, which is going to be the very first element we're going to actually look at for this pass. So as we get further in with our passes, we don't have to look at as many elements because the first couple ones are already going to be sorted. What I'm going to do after I've set up min index here is I'm going to go ahead and do a loop to find our minimum value. And we'll do this as a for loop as well. And what I'm going to do is create another variable called j, and I'm going to initialize it to I plus 1. We're going to go and loop as long as j is less than the length of our array. So sort array.length, and each time through we're going to go and increment j. And what we're going to do inside of this inner loop here is just compare the value that's in element j with the one that is our previously found minimum and see if we find something that's smaller. So we'll do if sort array sub j dot compare to, and we're going to go and compare it to sort array sub min index. If that is less than 0, then what we're going to do here is update min index because our new one is smaller. So we'll say min index equals j. So we're going to keep on looping through everything until we've checked it all and we've figured out which one is going to be our smallest index location, and that's in min index. And then what we're going to do after that is swap things if we actually need to swap. Now we're going to actually just do a quick check here just to make sure that min index is not I, because if it is, then we don't even need to go and swap. but I'm going to say here if I is not equal to min index, then we're going to do our swap, and we'll need to have a temp variable for that. So I'm going to say var temp equals sort array sub I, and then we'll go and say sort array sub I equals sort array sub min index. And then we're going to go and say that where we grab the minimum value from, so sort array sub min index is going to be equal to our temp array. I'm just going to go ahead and plop in some Javadoc here. And now we have our iterative implementation done. For our recursive implementation, I'm actually going to start off by creating a helper method. So it's going to be a protected method because I'm not really intending for this to be publicly used. It's going to be static, and we'll have our same generic specifications. And what this method is going to do is it's going to go through and find the index where the minimum value lives. So rather than using a loop like we did with our insertion sort implementation, this is actually going to be a recursive method that will take care of that for us. This is going to require 3 parameters. We're going to have the array that we're trying to go and find the minimum value from. We're going to have an int with the start index we should be looking at, and an int with the end index that we should be looking at. We're going to go and begin by checking for our base case, and that's where we're just checking one element. So our if here is going to be if start index is equal to end index. And if that's the case, then we're just going to go ahead and return start index. After that, we're going to have our recursive call. And so we're going to find the minimum from the rest of the array. And we're going to go and place that here in a var that we're going to call min index rest. We're going to set equal to return value from calling selection sort dot find min index, and we're going to go and pass it our min array. We're going to start index +1, and then we're going to keep end index as is. Once we have min index rest, what we're going to do is just go and check to see if the value that we're getting from there is less than the value that's in our current start index. And we'll just use a ternary operator and do this all in our return statement here. So what I'm going to do is compare min array sub start index with the compare2 method against min array sub min index rest. And if that, we're going to see if that is less than 0. If it is, then we're going to go and return start index. Otherwise, we'll return min index rest. And that's all that we have in this particular method. I'm just going to go and give it some Javadoc. Most of this is pretty straightforward here. Start index is going to be the start index for search. End index is going to be the end index for search. And we're going to go and return the index containing the minimum value. With that out of the way, let's go and work on the recursive part of our selection sort algorithm. This is going to be protected because we'll create a public facing method here. Static, standard generic stuff. And I'll have a void return type, and I'm going to call this recursive selection sort, and it's going to take 2 parameters. The first is going to be the array of type T that we're trying to sort, and the second is going to be an int with the current index that we're going to look at. Inside here, we're going to begin by checking for our base case, which is when our current index gets to be the size of the array itself. Current index is basically our starting position that we're going to be using here. So if current index is equal to sort array dot length, then we're just going to go and return. Assuming that they're not, what we're going to do is go and find the minimum index. So I'm going to go and create this var here, min index, and I'm going to set it equal to the return value from calling our find min index method. I'm going to go and pass it sort array, current index, and then for the end index, that's going to be sort array dot length -1. We don't want to have it go and try to sort anything past the end of our array. Next, we want to figure out if we need to go and swap things. So what we're going to do is check to see if the current index and the minimum index are the same or not. So if min index is not equal to the current index, then we're going to have to go and do a swap. And we'll use a temp variable as part of this swap here. We're going to say var temp is equal to sort array sub min index. Sort array sub min index is going to be equal to sort array sub current index. And then sort array sub current index is going to be equal to our temp. After we do that swap, we're going to go and place a recursive call. And what's going to happen here is that basically each time we go and sort one element further in. We're going to do selection sort dot recursive selection sort, and I'm going to pass it sort array, and then for the second parameter that's going to be current index plus 1. I'll go and give this some JavaDoc. So this recursively performs selection sort. T is our type of data being sorted. Sort array is the array being sorted, and current index is the current index that is to be sorted this pass. I'm also going to go and create a public method that will go and simplify things a little bit, because it'll specify the correct value for current index without relying on a user to actually go and do that. So I'm going to go and actually just copy and paste the JavaDoc and the header for our protected version here. And I'm just going to go and fix that up here. So we're going to make this be public instead of protected, and we're going to go and get rid of the current index parameter. And inside the body of this version, we're just going to go and call the other version. So we'll say selection sort dot recursive selection sort. We're going to go and pass sort array, and then for our current index, we're going to start off with 0. So let's go and see how this works when we go and sort things. Let's go ahead and call our recursive method, since we just coded that one. So we'll say selection sort dot recursive selection sort, and I'm going to go and pass it numbers, and we'll run that. So you can see the values we had before, and then how they're all nicely sorted afterwards. And since we didn't run the iterative one yet, let's go and do that too. So we'll say selection sort dot iterative selection sort, and I'm going to pass this numbers as well. And you can see that it also goes and generates sorted results. Selection sort doesn't have the best performance. As you can see, it's big O of n squared for everything. And that's really comes down to the fact that we have to go and make those n-1 passes, and each time we have to go and look over n elements to figure out which one is smallest. Now, just one thing to keep in mind here is that, even though these different algorithms have the same big O time complexity, there are some differences in terms of the constants that would be with these. So they're not all going to perform identically. And especially as we deal with larger data sets, those little constants, they will start to go and make some sort of difference. Pros and cons of working with selection sort. As I mentioned, there are some differences with time complexity that might not be entirely obvious. One of them is that selection sort does actually go and require fewer swaps than if we were to go and do something like bubble sort that we're going to take a look at next. Selection sort also works pretty well if we're going to go and work with nodes. We can go and make those swaps with our values. The big negative to it is just the fact that it has pretty poor performance. It's that n squared time for best, worst, and average cases. Next, let's take a look at the bubble sort algorithm. The final sorting method that we're going to take a look at in this lecture is bubble sort. Bubble sort works by going through and comparing pairs of items. We're going to go through and look at the item with the one right next to it and see if they are in the correct order, where the smallest one comes first. We're going to go and do n-1 of these overall passes. We have an outer loop for that, and then inside there's an inner loop that goes and compares each item with the one next to it. What happens, as you can see with the animation that's showing here, is that the largest values get pushed to the right. So at the end of the first pass, the very largest value is going to be in the last element. By the second pass, the second largest element will be in the second to last location. And so on until we go and end up with everything being sorted here. Compared to some of the other implementations, bubble sort can have a lot more swaps, especially compared with what we saw on selection sort. One of the challenges when we're trying to sort reference type objects, which includes things like strings and our wrapper types for integer and double, anything that would involve basically being stored through the use of a generic parameter, is that potentially, at least in theory, we can have values stored that are nulls. Now, we may choose to go through and filter these null values out through the operation of our code. But if we actually have null values stored, we run into problems if we try to go through and use the compare_to method built into the object itself to try to figure out how to sort things. If we try to go through and call compare_to or any other method on a null object, we're going to get a null pointer exception. So we would have to go through and write additional code that would go through and check for if we have null values before we try to go through and use compare_to. And that kind of tends to make things be a little bit messy. If we have a case where we potentially have null values stored in our data, we want to figure out some way that we can go and sort them that isn't going to cause a problem with those null values. The mechanism that we're going to use to take care of nulls is what's known as a comparator. So comparator is something that's built into the java.util package, and it's an interface that we can go and implement to provide custom code for how to go and compare and then sort objects. Java gives us some built-in comparators that will handle cases where things might be null. Inside of the java.util.comparator class, there are two static methods that are going to be really helpful for us in dealing with nulls. They're called nulls first and nulls last. And as you can kind of guess from the names, what they're going to do is sort nulls so that they either come first before all the other items or last after all the other items. We can go through and get a comparator that goes and handles nulls by going and calling the nulls first or nulls last static method. Now, that isn't quite the end of things. When we go and call these nulls first or nulls last methods, they do take a parameter, and that's going to be a comparator that we want to use for everything that is not null. So if we have an actual string or a capital I integer, how do we want to go and sort those? While we can go and write our own comparator, often that's something that we don't want to get into. It can be kind of involved to go and code that up. Java.util.comparator includes another static method called natural order, and this one does not take any parameters. If we go and get a natural order comparator, what's going to happen is that when Java tries to go and compare things, it's just going to rely on the existing compare_to method that's part of the class that we're trying to go through and sort. So what will happen here is if we go and combine nulls first or nulls last with natural order, is that it'll go through, check to see if things are null. If so, it'll go and position them so they're either up front or at the end. For the non-null things, the way it's going to go through and sort those is by going through and, when we say natural order, looking at the compare_to method that's already there on our object. So the standard wrapper types and things that we're likely to use are already going to have compare_to implemented, so we don't have to do anything special. If we go and create a custom class, we could also go and write our own custom compare_to method there, and if we said natural order, it would just go ahead and use that. So we're going to go and rely on natural order to go through and handle really the bulk of our sorting, anything that is not null. Let's go ahead into Eclipse and we'll see how we can code up bubble sort. Once we have our comparator object, we need to actually go and pass that to another method to be able to go and compare things. The method that we're going to go and pass it to is a static method in the java.util.objects class called compare. This method takes 3 parameters. The first 2 are going to be the objects that we're trying to compare, and the third is going to be our comparator. This method basically works like compare_to, except for, because the way it's set up here, it is not going to throw a null pointer exception if we have a null value. We're going to see the same type of return values from this as we would with compare_to. It's going to be an int. It'll give us a negative number, value less than 0 if the first object should come first. It'll give us a 0 if the 2 objects are equal. It'll give us a positive number if object 2 should come first. The first version of bubble sort that I'd like to look at is an iterative implementation for working on values in an array. Here, for the example code that we're going to be working with, I'm creating an array of 20 of the integer wrapper type objects. 19 of those elements are going to have random numbers between 0 and 100. The last one is going to have a null value stored. Let's go ahead and code up our method to go through and sort the contents of an array. I'm going to have this be a public method, and I'm going to make it be static. We'll go ahead and pass the array that we're trying to sort as an argument when we go and call this method. I need to make sure that I have a mechanism available to me to go and sort whatever type of item is in the array. So I'm going to go and provide a generic for this method here, and I want to say that t extends comparable, and that basically we're dealing with comparable implementation here for something that is the same or a superclass of t. So this is the same type of language that we've been using all along here to get access to the compare_to method. This method is going to return a void return type, and I'll call it iterative array bubble sort. And then I'm going to take this t type array, I'm going to call sort array as the item that we're actually trying to go and sort. Inside my method, I'm going to need a pair of loops to go and perform the bubble sort. The first one is going to loop for n-1 passes, where n is the number of items that we have. The reason why I'm doing n-1 is that basically by the time we would get to the nth pass, our data is already going to be fully sorted, so we can go and skip that very last pass. For this loop here, I'm going to do a for loop. I'll create a counter variable I. I'm going to loop while I is less than sort array dot length, which is basically the number of items that we have, that's our n, minus 1. And then I'm going to go and increment I. Inside of that, I'm going to have another for loop. And this one is going to go and look at each pair of values to figure out if they need to be swapped. We'll do a for loop here. I'm going to call this variable j. We'll start off with it at 0. And I'm going to loop while j is less than sortArray.length minus I minus 1. And we'll go and increment j each time. The reason why I have the minus I part here is because after we go and make a pass with our sorting, the highest value is going to be in the last element of the array. I don't need to go and sort that element again. It's already in the spot where it needs to be. So I can go through and slightly shrink, in this case by 1 element, the values that I need to go through and sort on the next pass. And that is just going to go through and continue. We can go through and reduce by 1 the number of elements that we need to go and sort with each pass, and the minus I takes care of that. Inside of this inner loop, we need to go and compare the values from our 2 neighboring elements to figure out if they need to be swapped. For this, we're going to make use of the objects.compare static method with a comparator. So this is going to be a little bit complicated with this line here. Let's walk through what we need to do. For our if statement, I'm going to go and call java.util.objects.compare. So this is kind of like a compare to method on an object, except for here this is actually a static method. And this is going to go through and allow us to handle cases where one or both of the objects that we're trying to compare are null, since we're not actually going through and calling the compare to on the object itself. I need to go and give 3 parameters to compare. The first is going to be the first item that I want to compare. So for this, I'm going to say that I want to do sort array sub j, and my second item is going to be sort array sub j plus 1. The fact that I'm doing the j plus 1 here is why I have the minus 1 for where I'm going and looping for j here. And we talked about the minus I was since we didn't have to go as far in with each pass. The minus 1 is to ensure that I can legally go and do a plus 1 here. The third argument that I'm going to have to go and provide to the compare method is the comparator that I want it to go and use to go and compare those values. Since we want to be able to go through and handle null values, I'm going to go and use one of the null aware comparators. And there's 2 versions basically that are built in. Nulls first, which will go and put null values first when we go and sort, and nulls last, which will go and put them last after all the non-null values. Let's go ahead and use nulls first. For this, it's going to be a static method that I need to call. It's going to be java.util.comparator .nulls first. And this is a method, so it's going to have its own set of parentheses. Inside the parentheses for nulls first, I need to go and provide another comparator. And this is going to be what's going to be used to compare values that are not null. I really don't want to have to go and create my own comparator. I really just want to go and use the compare to method that's on my existing objects. So in order to go and do that, I'm going to go and use the natural order comparator. Now, with these statements here, just be aware I could go through and import java.util.comparator and save a little bit of typing here, but just to avoid any confusion, I'm going through and fully qualifying the names. So here I'm doing java.util.comparator.natural order. This one doesn't go and take any parameters, but what it does do is it goes and says use the compare to method on these objects if they're not null to go and figure out how to compare them. The compare method from the objects class is going to return an int value, the same as if we were actually calling compare to. If the value is less than 0, then it means that our first thing, sort array sub j, should come first. If it's equal to 0, it means that both of these values are the same. And if it's greater than 0, it means that our first item, the sub j here, should come last when we go through and sort things, or at least after the j plus 1. So we need to go through and compare here the actual return value that we get from the compare method. And what we need to do here is we're going to go through and see if the value is greater than 0. If it's greater than 0, that means that j plus 1 should come first and then j. In this case, we're going to have to go and swap those values. So what we'll do here is write 3 lines of code to go and perform that swap. First, we'll go and create a temp variable, and that's going to go and store what's in sort array sub j plus 1 right now. Then I'm going to go through and set sort array sub j plus 1 equal to what's in sort array just plain sub j. Finally, to finish the swap, I'm going to do sort array sub j is equal to temp. And that'll go through and complete swapping the items around. So inside this inner loop, within a pass, we'll go through and compare each of the adjacent items, swap them around so that the smaller number, or if we're looking at like strings, the thing that's closer to A is going to come first, and then that the higher valued thing is going to come second. And we'll just go through and do this until we have n-1 passes, and at that point, everything will appear in sorted order. Let's go ahead and provide some JavaDoc for this method. So we're going to go and iteratively performs bubble sort. Our param t here is the type of data being sorted, and our sort array is going to be the array being sorted. And then let's go up, and where in our main method we have this spot that we're supposed to call our sort method there, let's go ahead and actually do this. So I want to go ahead and call this method, and it's a static method, so it's not part of any instance. I'm going to use the name of my class here. So it's going to be array bubble sort dot, and it's the iterative array bubble sort, and I need to go and pass the array that I'm trying to sort. So I'm going to go and pass numbers. Let's go ahead and run this code. And you can see here we had these values before, and they're just sort of all over the place, and the last one was null. Once we go and sort them, the positions are such that our null comes first, and then after that, things are in ascending order. You can see that in some cases here we actually had duplicate values, so we had like 251s, but that's okay. That's what was in the original source data set. So this is how we can go through and implement bubble sort iteratively. While it is theoretically possible for us to go through and do a recursive implementation of bubble sort, it actually ends up being more difficult to go through and implement, and there's really no benefit to it. So we're not even going to bother looking at a recursive implementation of bubble sort. While we're not going to look at a recursive implementation of bubble sort, we will take a look at an implementation that's done on a list rather than an array. Here I'm going through and creating a singly linked list with 19 random numbers in it, and then I'm going through and adding the value null. I'm going to create a static method that will go and sort the values that are inside of that list. Our method for working with the list is going to be iterative, just as when we were doing the array. For our method here, it's going to be public and static, and we need to go and provide a generic parameter for the type of value that we're going to store in our list. As we did with the array, we're going to say that we want t, that goes and extends comparable, and then for the generic parameter on comparable, we're going to say that it's either t or a superclass of t. Our method is going to have a void return type because it's going to manipulate the list directly, and I'm going to call my method iterative list bubble sort, just so I've got that full descriptive name. I need to go and pass a list to this method here, And what I'm going to say is that I want to take anything that goes and implements list interface, which is the one that we actually coded up earlier this semester here. I'm going to go and call the parameter sort list. The basic mechanics of sorting a list are going to be pretty much the same as when we were sorting an array. We'll have a pair of nested loops. The first one is going to control how many passes we have, and we want to loop for n minus 1 passes. I'm going to do a for loop for this, and we'll say int I equals 0, while I is less than the size of our list here. So this is going to be a little different. We'll do sortlist.size rather than sortarray.length. But I'm still got the -1 part here, and I'm going to go and increment I. Inside, we're going to loop to compare values within a single particular pass. And I'll do another for loop here. I'm going to call my counter variable j. We'll initialize it to 0, and I'm going to say while j is less than sortlist.size minus I minus 1. And each time through, we're going to go and increment j. And then inside this inner loop, we can go and actually compare our values. And we're going to use the objects.compare method with the same type of comparators that we did with our array implementation. So I'm going to write an if statement here, and I want to say if java.util.objects.compare, and that's a static method, so I don't need to instantiate anything here. For the first value that I want to compare, I'm going to go and get element j. So I'll say sortlist.get and then j as my argument. For the second one here, it's going to be sortlist.get of j plus 1. And then my third argument here is going to be the comparator that I want to use for things. And this is going to be where we want to allow nulls. So I'm going to say java.util.comparator. And we'll do nulls first. And then I want to go and have it use the natural order, so essentially the compare to method, for going and sorting anything that is not null. So inside the parentheses for the argument to pass the nulls first, I'm going to say java.util.comparator.natural order. And then I'll need to go and check the value that I get back from the compare method here to figure out what to do. And we want to look to see if the value is greater than 0, which means that j should come after j plus 1. So what we're going to go ahead and do in this case here is we're going to go and swap our values. I'm going to go and say that I'll have a temp variable, and it's going to store the value that's in sortlist.get for element j plus 1. Then we're going to go through and actually set things here. So we'll do sortlist.set, and I'm going to set j plus 1 equal to the value that's in j. So for the value I'm going to set to, I'm going to say sortlist.get with an argument of j. I need to finish going and setting j then. So sortlist.set with my first argument of j, and I'm going to go through and set that to the value of temp. Let's go ahead and provide some JavaDoc for our new method. We'll say that it iteratively performs bubble sort, and then we'll go and list our generic t as the type of data being sorted and our sort list as the list being sorted. And then we'll go ahead and call that method from up in our main. So again, since this is a static method, I'm going to use the name of my class here, list bubble sort dot, and then we'll call it the iterative list bubble sort. And I'm going to go ahead and pass it my list that I'm calling numbers. And then we can go ahead and run this code. You can see the values I had before things were sorted, and then afterwards with the null first because I used the nulls first comparator. In this case, we're not going to do a recursive implementation of the bubble sort method. And the reason why is basically nobody really does a recursive implementation of it. It's very rarely coded recursively because there's no advantage to doing so. The recursive implementation doesn't perform any faster, and it's more difficult to go and understand how you would go and implement it with the having things recurse than just doing an iterative implementation. Looking at the time complexity of bubble sort, we see that its best case is actually big O of n. And that's a little bit deceptive in terms of what sort of performance we can really expect from bubble sort. For our best case, keep in mind that the values are already sorted in the correct order, so all we have to do is just basically make a pass to go and figure out that we don't need to go and move things around. Average case and worst case implementations are both big O of n squared, but again, the constants here do sort of matter when we're comparing bubble sort against other implementations. Bubble sort, because we have to go and move items one position at a time, we tend to end up going and doing a lot of swaps when we go and use bubble sort and we do have to move things. So for that reason, bubble sort tends to be disfavored, especially if we have larger data sets. It's easy to understand and implement, and it's a pretty simple algorithm, so those are positives when we're dealing with smaller data sets. But as we start to get to larger numbers of items that we have to sort, all those swaps start to compound. Its performance just isn't as good as some of the other alternatives that we've been looking at. For this lecture's participation project, you need to download the participation project starter code from eCampus. Inside of there, you'll find a sortable linked list class that you need to modify. Inside of that class, you should add a new method to go and sort the values, and call this method sort. What this method needs to do is it needs to go and take the values that are currently in the list and sort them. The list itself should be sorted when you're done, so that if you go and retrieve whatever item is in element 0, that's going to be the first thing from our sorted results. You can use whichever sorting method that we've looked at in this lecture that you prefer, but your approach should go and allow null values to be stored inside the list. And when things are sorted, those null values should appear last at the rear end of the list. When you turn in this project, you should only submit your modified sortable linked list class. That's the end of our initial look at sorting algorithms. We've got more to come still. If you have any questions on this material, please join our Q&A session or send me an email. Thanks, and have a great day.